Which would you prefer? New York or Mandalay?
Oh, please don't joke about it. Mrs. Van Hopper's waiting, and I'd better say goodbye now.
I repeat what I said. Either you go to America with Mrs. Van Hopper, or you come home to Mandalay with me.
You mean you want a secretary or something?
I'm asking you to marry me, you little fool. Come in.
If you love listening to this show, please consider giving a rating and a review on Amazon Alexa or wherever you listen. We want to continue bringing you this amazing content, and part of our ability to do that means that we need a big audience. Now, it may not seem like much, but rating and reviewing the show will help more people find us, just like how you found this show. Simply on any podcast platform, search for our show, scroll down to the bottom, and push 5 stars. It's that easy. Thanks for supporting the show. Today, I'm joined by Federico Faggin, a physicist, engineer, inventor, entrepreneur, and an author and the designer of the world's first microprocessor. Welcome to the show today.
Thank you.
Now, you've developed everything from integrated circuits, microprocessors, microcontrollers, PCs, personal communication, as well as analog chips, the touchpad, touchscreen, to image sensors, digital cameras, mobile devices, and many more. And of course, you've won everything from the Marconi Prize, the Kyoto Prize, the Lifetime Achievement Award from the European Patent Organization, the National Medal of Technology and Innovation from the President Barack Obama, as well as being inducted into the National Inventors Hall of Fame. Now, going to your kind of earlier origination is you were born in Vicenza, Italy, and you study physics, correct?
Yes, correct.
I'm curious. What made you move to Silicon Valley in the 1960s? And I believe at that time you had kind of recently designed an experimental transistorized electronic computer.
Yeah, my first experience was at Olivetti after high school, a technical high school. And there I designed a small experimental computer using transistors. And I designed about 60% of it and built it with 4 technicians. I was 19. And that experience really set me for life, I would say, because without that, I would not have been able to design the world's first microprocessor. The coming to the US was fortuitous because I was working for SGS Fairchild, which was connected, 30% owned by Fairchild Semiconductor, which is the company that invented the integrated circuits here in the Silicon Valley, based in Mountain View. By the time I joined them, and I worked in the R&D of R&D department of Fairchild, and there I developed the MOS Silicon Gate Technology, which was a new way to make MOS transistors. MOS transistors in those days were really used for only a small percentage of the integrated circuits. Bipolar transistors were the mainstay of the technology in those days. 95% of all production was bipolar. But eventually, Silicon Gate took over the entire industry of integrated circuits. Practically everything 15 years later was made with Silicon Gate technology, the technology that I invented there in 68. Intel started with that technology, and I joined Intel in early 1970 to design the first microprocessor that was made possible by this technology, because this technology offered 5 times the speed and twice the density, twice as many transistors for the same cost, for the same area, chip area. So it was the only way that we could at that time build an entire CPU, central processing unit of a computer, into a chip.
So again, I think you outlined many of the early key sets of inventions and contributions that you made. You mentioned the MOS Silicon Gate Technology at Fairchild, including the product 3708, as well as the commercial IC that was developed in 1968. You mentioned, after you joined Intel, you created Intel or contributed to Intel 4004, Intel 8008, Intel 80 and 80. So a lot of these are really, I think, for those that are listening that are, let's say, less than 50 years old, may not be as familiar with some of these kind of predecessors, but yet they were so critical to the foundational infrastructure of what we're actually taking advantage today. So for those that are not as familiar, can you kind of give some fundamentals around why some of these earlier developments and inventions were so critical for the kind of technologies that we have today?
Yeah, well, the integrated circuit, which was developed in the early 60s, the first integrated circuit was commercialized in 1962 by Fairchild using bipolar transistor. There was a way to put in a single chip, not only the transistors, but also the resistors, perhaps capacitors, all the other components necessary to make, for example, a logic gates or an amplifier, an operational amplifier, for example. So that technology was really the seminal work of Fairchild in those early days. Then MOS technology using transistors that were simpler came out at about the same time. But those transistors were difficult to make reliably, and they were very slow. And they were not living up to the promise. And so with this new technology, silicon gate technology, now we could put a lot more transistors in a chip. So we went from, say, 500 or 700 or 800 transistors to about, in 68, to about 1,500. And by 1970, we could put about 2,500, which is really the kind of minimum number of transistors to make an entire function of a central processing unit in a single chip. Why a single chip is important? Because if you divide the function of a CPU into several chips and you have to then send signals in and out of different chips, those signals will slow down the entire processor, because to go in and out of a chip, you lose a lot of speed. So it was essential to be able to do a single chip CPU to maintain the speed, which is so essential to do with software what before could be done only with hardware. So that was the essence of the invention. Was finally the entire function of a central processing unit could now be put into a single chip, and then the rest of it was already available: memories and circuits for input output, which are the other two building blocks of a computer. Now, 10 years later, the entire computer could be put in a single chip of the same size of the original CPU. And those were called microcontrollers. They came out around 77, 78. And those were the next step. And of course, by that point, when you can have an entire computer in a little piece of silicon, we can put compute power into pretty much any object, from from a toothbrush, the most trivial application. But in the toothbrush, the microprocessor generates all the signals to make the brush vibrate, to keep track of time, and do all the kind of function that you would have in an electric toothbrush, all in a little chip that dissipates extremely low power, and you can do a job that was unthinkable when computers were as big as a room or as big as a big box. How could you put a big box inside a little toothbrush, right? So that the advantage of integration is the speed, the cost, the size, occupy, and the power dissipation. So now computers are sold literally by the billions a month. So, when of course in those days, thinking of selling 1 billion components would have been unthinkable, because the entire world market of components was, in 1970 was of the order of 1 billion for the entire world. and now you have chips that have 10 billion transistors, of random logic or mixed logic and memory. And you can have on your pocket, you can now have floating gate transistors that are they are silicon gate transistors that can do non-volatile memory, and you can have up to 1 trillion bytes of non-volatile memory in your pocket. In 1975, that would have taken a building full of disk drives with a cost of several $1 million just to have what you now have in your pocket for $30.
I mean, I think, many of us don't really fully understand or appreciate the kind of scale that we're talking about. Of course, fundamentally, we're talking about the Moore's Law, but for every stage of the Moore's Law and the marginal cost and the miniaturization happening, it's not just at the chip level, but it's really the entire infrastructure. To run these fabless operations, you need to retrofit all the machinery. So every time you run new sets of, I think we're down to almost, 2 millimeters or whatever it is, that it's a huge investment over the decades, so that we got to this point, to your point, where we have, in the billions and trillions, that's just within our pocket or within an IoT device. I wonder if you kind of look back at the span of your career, what were some of the key, I don't know if it's inventions or key infrastructure upgrades that really enable for us to, take advantage of what it is today?
You may also like our quarterly Ask Your Perkins event that brings some of the most notable experts and category-leading startups in their area of sustainability and human survival on Earth and in space. To register, visit askyourperkins.com/events.
Basically, the driving force has been the reduction of the size of the transistors. So, for example, bipolar transistors, where I give you orders of magnitude because it would be too difficult otherwise to appreciate it. So, a bipolar transistor was of the order of say 20 micron. Okay. A MOS device was of the order of 5 micron. Now we are at the order of 5 nanometer. So 5 nanometers is 1,000 linearly 1,000 less than 1 micron. There are 1,000 microns per millimeter. And but of course, what matters is the area. So the area goes with the square. So a transistor today is 1 million times smaller than the transistor that I use in the first microprocessor, the 4004. So that gives you an idea. And of course, the microprocessor was much smaller than what you could have done with bipolar technology, because bipolar technology, instead of 5 microns, would have been 25 microns or something like that. And so, you couldn't put a CPU on a chip. The chip would have been way too big. It would be impossible to manufacture. And so the game is being reducing the size. Now we are down to a size which is very close to the physical dimension of atoms. And an atom is of the order of 0.1, 0.2 nanometers. So, and you need to have a statistical significant physical structure in order to make the function of a transistor, which is a switch turning on or off, as simple as that. But you really need quantum physics to work for you. And so it's hard to imagine that we can get below 1 to nanometers as the minimum size. So at 5 nanometers, we are very close to the limit. That's why we need to find new ways to make computers that can run faster than what we can do with traditional transistors, which are MOS transistors. They could be reduced in size because they are planar devices. So they work on the surface and the interface between an insulator, which is early on was silicon dioxide, and the silicon. And those transistors could then be reduced quite easily, where bipolar transistors, they are bulk devices. They also work in the vertical dimension, not only in the surface. And so those could not be reduced beyond a certain point. And so eventually they disappear. They were taken over by MOS technology. And so in the story, the story was first bipolar, then MOS with metal gate, then MOS with silicon gate that remove all the problems with metal gate, and then MOS silicon gate all the way until about 10 years ago, when we had to resort to new materials for the oxide and new materials for the gate, with properties that were not in the silicon dioxide. So all the new devices, especially the ones that are built below 10 nanometers or at 10 or below, they are vertical devices. They are they are very sophisticated construction. They have a very sophisticated construction, and every new technology requires refinements that are very costly to do. In fact, Intel itself, that has been the leader company in manufacturing technology, they kind of lost the recipe at 10 nanometers, and the lead was taken up by the Koreans and by the Taiwanese. And so now people use technologies that don't even exist in this country, unfortunately. So that's how far and how fast we have gone.
So you mentioned this notion of 0.1, 0.2, where we're starting to get into atom level. So essentially, quantum mechanics, as you mentioned before. And what's interesting is you have a perspective that very few people have. Not only you've lived a certain lifespan in a very critical time period, but you're very much the pioneer in many of these technologies as well. So I wonder how you see some parallel to what's happening on the quantum computing side, as I think there's a lot of different approaches, a lot of different technologies, a lot of different components. Again, we're not quite where we are with the classical computers that we're talking about today, but when you think about the kind of roadmap to maturity and miniaturization that quantum computing is headed, what are some things that come to your mind, and some of the things that you would tell others?
Well, quantum computing promises to go beyond classical computers in terms of speed. Not in terms of what it can do. You can do with a classical computer anything that a quantum computer is imagined to do for now, except that the quantum computer will perform operations in parallel. So it can perform them much faster than they can be performed with classical matter, in a way, using quantum matter. And in order to have quantum matter and the properties of quantum matters, you have to go down to very low temperature, typically very close to the absolute zero temperature, which of course is a hard thing to do, to keep that temperature and to have systems that dissipate some power to work under those conditions. And the technologies that are going to emerge are still being tested. Really, we are still in the early phases. We haven't found yet, I don't think, in quantum computation, the equivalent of the planar process, which was the technology in which you could make transistors all in a slice of silicon, in a single slice of silicon called wafer, where you could put many transistors and then you could connect the transistors together in that same slice of silicon, therefore make an integrated circuit. So all that technology that eventually took years to arrive to this culmination of ideas, that was the planar process, invented by Jean Erny, by the way, a Swiss engineer that was one of the 8 founders of Fairchild Semiconductor. And this process really was the key to everything that happens afterwards. When it comes to quantum computers, there are different approaches, using photons, using using quasi-particles. It's still very much in flux, and it may take another 5 or 10 years before we are at the level that we were in 1962 or 1961 with silicon technology. But it will happen. I expect it to happen. The investment is huge in that direction. The payback is essential because we want computers that are ever faster. Just think about it, that the power consumption expected in 2025 in the US used by the computers in the cloud computing centers will be around 20% of the total usage of electric power in the US. I mean, that's a staggering number. Basically, we're saying that 20% of all the power goes into the services that we use through cloud computing, from Alexa to supercomputers that we use for all kinds of applications. So we are talking about a problem here that is not going to go away. In fact, it will get worse because, as I said earlier, the conventional technology is stopping off. It's just it's just growing a little bit every year, but not as much as it used to be. Moore's law has reached its limit. So quantum computers is the savior, so to speak. And in a sense, the dramatic thing is that nobody knows where that computation is done. It's not done in this space-time, because in this space-time, you can only do classical computation, the computation of our traditional computers. You cannot do that computation. You get the results, you start the program, you set up the program, you start the program, and you get the result in this space-time. But the computation is done who knows where. There are, basically, you meet the fundamental problem of understanding quantum physics, and nobody does. Nobody understands what's going on. And of course, that's also the mystery of consciousness. It is connected with the quantumness, the fundamental quantumness of reality.
So there's so much to cover, and we didn't even get to cover Zilog or SignNets or Synaptics as an example. But since you mentioned consciousness, which has been quite a passion for you, and there's a foundation that you're running that's specifically focused on that, can you define what you mean by consciousness, and what exactly is the foundation working towards?
Okay.
Don't forget to visit astroperkins.com to register for our next quarterly events. Past and current speakers include Julianne Hough, actress, dancer, and winner of Dancing with the Stars; Damian Vaughn, former NFL player; Neil Gregory, Chief Thought Leadership Officer at the IFC World Bank, and many more. To register, visit astroperkins.com and click on Events.
So consciousness is the ability that we have to have a sentient experience. In other words, we know because we have sensations and feelings. So we know because we have an inner world full of sensations and feelings, what philosophers call qualia. That's how we know. We don't know. We have signals in the brain, but the signals in the brain cannot be the sensations and feelings that we have. Where are the sensations and feelings coming from? That nobody understands its origin. Now, together with a professor of physics actually is a world authority in quantum information, Professor Dariano is the head of quantum physics group of University of Padua. We wrote a paper that will be a chapter in the book also. And basically, we have a theory now. This theory is that consciousness is a property of a quantum system which is in a pure state. pure states are very special states in quantum physics. It's difficult to define them, but the definition which I give you, but it baffles you because it appears incoherent, is that a pure state is a state that cannot be expressed as a combination of other pure states, but it emerges by these other pure states combining via entanglement. The entanglement is the property that makes quantum computer work, is the property that has baffled physicists, that people in physics cannot understand. I mean, they have to take it for good because it exists, and you can measure it, and there is no question about it, but it is incomprehensible. And so entanglement is the fact that, for example, electrons that interact with each other, they have now they have joint properties that are retained even if those electrons now are taken apart. But those properties, however, still obey the probabilistic nature of quantum physics, and especially the complementarity of quantum physics, which says that you can only know the position or the momentum, but not both simultaneously. And so what happens is that when those particles are taken apart, maybe one at the other side of the galaxy and the other one here, when I measure a particle here now, the other particles knows that I have made a measurement. And that knowing that I made a measurement means that it will show the correlated value that I measure here. And since I don't know what will show up here will show up a probabilistic value. So how can that particle know that I measure up instead of down in order to be down instead of up? Because that's the corresponding entangled variable on that particle. So that's a big mystery. That actually was such a mystery that Einstein in 1935 used that to show that quantum physics could not be complete. If there was something missing, we were missing something. Well, we didn't find anything missing since that time, but we found that entanglement, which is the fundamental property that we're talking here, exists. And it is at the basis of all these extraordinary things that quantum physics can do, including consciousness, because it is at the foundation of why, when you combine pure states, and these pure states are entangled, they can create new pure states that once they are created, they can no longer be expressed as combinations of those states. So I mean, in other words, that's a property that allows a whole to be more than the sum of the parts. In a classical system like a computer, the whole is simply the sum of the parts. And our consciousness is a whole that is more than the sum of the parts, because it can affect the parts, because it is independent from the parts. Where in a computer, there is no whole that can affect the parts. So the parts simply, they appear to behave like a whole, but that whole is simply the name of the parts. And that's a big difference.
So I wish
will never be conscious.
Yes. So again, I wish we had more time to explore, but we're almost out of time here. So as we advance in not only quantum physics, but with the application of quantum computers and this notion of pure state that emerges from entanglement, is it possible that we can have better insights into this notion of consciousness? And more importantly, could we potentially even replicate it in an artificial substrate, including mind uploading and other forms that are, transhumanism?
Yeah. So basically, this theory is saying that consciousness can only exist in the quantum reality. The quantum reality, which is today described by Hilbert spaces. Hilbert spaces are n-dimensional, many-dimensional spaces with the complex dimensions. So it's a mathematical, very, very, very powerful mathematical method that allows you to express pure states, mixed states, the things that happen within quantum physics, different kind of transformations and so on. But then there is the so-called collapse of the wave function. And the collapse of the wave function in this theory occurs because certain systems, quantum systems, that are in a pure state, and by being in a pure state, they are conscious, meaning they have an experience of that pure state. So they actually experience the qualia there is this inner property of this stuff that carries this pure states, this energy that carries the pure state, that experiences itself. So the capacity to experience is a pure quantum property, and the quantum property then relies on this entanglement. And so that being the case, if you accept that, then a classical computer, will never be conscious. You will never be able to download your consciousness in a computer, like some people say. Transhumanism has this idea. Consciousness is private. The quantum information, which is the expression of a pure quantum state, that information is not clonable, is private, exactly like your consciousness. Your consciousness is a private to you only, meaning your experience can be shared with symbols, with information, by you describing your experience. But nobody can get access to that experience. If you open the skull and you measure signals, those signals are not the experience. Those signals are the outer information that whatever you can get from that experience. But that experience, being quantum, is a reality that is as information, is made of qubits, quantum bits, and a quantum bit is not clonable. And especially quantum bits which are entangled, where if you were to download your consciousness in a computer, classical computer, like people say, then that experience will be clonable. That because you can copy bits, you can copy programs, you can copy data which is in a computer. So it fails the simple test of privacy.
Fascinating. So with that, I have been joined by Federico Faggin, who is a physicist, engineer, inventor, and author of Silicon. Thank you for joining our show today.
I appreciate it. Thank you very much.
If you've enjoyed this episode, take a moment to rate our show on any podcast platform that you listen to. Scroll down to the bottom and push 5 stars. It's that easy. And as always, thanks for listening.